If this, then that. One of the most common things a software engineer will hear from their boss. If this happens, then we want our system to do X, Y, and Z. Well, in today's video, I'm going to break down an architectural approach to this request and provide you with a modular and scalable solution. Hey everyone, welcome back to the channel. Today we'll be designing and implementing an event-driven architecture that senior software engineers like myself use in the industry. As always, links to my GitHub can be found in the description. While this video will focus in on a specific use case, keep in mind that the logic and foundational components of this solution can be applied to many different use cases across any industry. For today, let's keep things as simple as possible so we can focus on the design patterns. When a file is uploaded to a specific location, we want to move the file to a different location. Maybe a user is uploading an image, and this image needs to be run against a machine learning model for object detection, and its output is returned elsewhere. Or maybe you need to collect log files and ingest them into a log analytics workspace to monitor hundreds of microservices. Whatever your specific use case is, the same principles will apply. The first thing we need to do is to define our approach to developing this solution. This is commonly referred to as our system design. Typically, you'll start by defining the system constraints and feature expectations with a stakeholder or group of stakeholders. Then you'll perform some estimations for things like system traffic, storage requirements, and throughput. Finally, you'll iterate through a high-level design and a detailed design with your team of engineers. In the spirit of keeping things as simple as possible, I'll walk you through my high-level design so we can get to developing. I'll be using Microsoft Azure as my cloud provider, but you can easily replace this solution with an AWS or GCP equivalent with some minor differences. We'll start with the system entry point, our storage account. This storage account will have two storage containers, one for input and one for output. The input container is where a user can upload a file. The output container is where a user will go to retrieve the file after our event-driven operations have been performed. For eventing, we'll use Event Grid. Microsoft's Event Grid is an awesome service that will allow us to create and send events at scale. This isn't limited just to storage accounts or file uploads either. You could just as easily create events based on other Azure services or even custom API requests from your own application. In this case, however, we'll be sending an event whenever a file is uploaded to our input storage container. For our core logic, we'll use an Azure Function. This is a serverless solution that allows you to write less code, maintain less infrastructure, and save on costs. Best of all, you can write your core logic in the most productive language for you. In this video, we'll be writing our logic in Python. The last component I'll mention is the storage queue. The storage queue will be used to hold any events that have been delivered by the Event Grid service so that the function can gracefully dequeue each event and act on it accordingly. It's important to note that you could just as easily exclude the storage queue and have your events sent directly to the function itself. But as with any architectural decision, there are pros and cons to each. A common mistake that junior and mid-level engineers make is assuming that simple and easy mean the same thing. In this case, it's much easier to exclude the storage queue and send events directly to the function. But what happens if the function crashed, or if the function is offline, or if it's in the middle of a redeployment? The events will never be delivered and files won't be successfully moved as we'd expect. Therefore, the simpler approach is to place the storage queue in front of the function so that even if the function does incur downtime, it can still dequeue events in order once it has recovered. We'll start our development by defining our cloud infrastructure in HashiCorp's Terraform language. Instead of manually creating resources in the Azure portal, we'll write our resources as infrastructure as code so that we can automate the deployment of these resources and follow best practices for maintaining them. If you're forking or cloning this repository, you'll need to include the GitHub action secrets with the same names you see here, but replace with the values specific to your account. Start by creating a .github folder to hold our GitHub actions. I'll create an additional folder called Workflows, which is where GitHub will look for YAML action files. We want to create a GitHub action that will deploy our Terraform code. In order for us to do that, we'll need a storage account in Azure that holds our Terraform state. When you run any kind of Terraform plan and apply from your own machine, the state file will be generated and stored locally for you. Since we want this to run in the cloud, we'll need a dedicated location for the state file, hence the storage account. My solution for this prerequisite is a bash script referenced within a GitHub action. This script will check for the existing resources in Azure to maintain our Terraform state, and it will create them if they don't already exist. Keep in mind that all Azure storage accounts must be uniquely named, so if this workflow is failing for you, there's likely another storage account that already exists with the same name. In the .github folder, I'll create a bash script called Terraform-backend. I'll add my shebang and create a usage function. To use this script, you'll need to call the file name, followed by a -g flag with the resource group name, and finally a -s flag with the storage account name. The resource group should already exist in the Azure portal. Below the usage function, I'll add a while statement that will get the value for each of our flags. Notice that the storage account flag includes 2 commas after the opt-arg variable. This automatically converts the input text to lowercase, since storage account names cannot include uppercase letters. Next, I'll add some checks that will call and return the usage function to our user if the resource group name or storage account name was not passed in correctly. Now we'll execute an Azure CLI command that will look for our storage account. If it's not found, the script will then attempt to create the storage account. Finally, we'll retrieve the storage account access key and execute a similar CLI command to look for our storage container. Similarly to the previous step, the script will attempt to create the storage container if it doesn't already exist. With our Terraform backend logic scripted, we can move on to writing our GitHub action that will call our script and deploy our Terraform code. In the Workflows folder, create a file called Terraform-Deploy. We'll give it a name and define the action to run on Workflow Dispatch. I set my environment variables at the top of the file for readability and maintenance. The first job we'll define is the Terraform plan. Terraform will look at our resources and generate a deployment plan for actually creating these resources in Azure. This deployment plan will be output to a file so we can reference it in the next job. The Terraform plan job has several steps. We'll check out our code so that the GitHub runner can see all of the files in our repository. We'll log into the Azure CLI using our credentials. We'll set up authentication to our Azure account by exporting specific variables. We'll pass in runtime variables for our Terraform code, such as the service principal secret and the name of our desired storage account. We'll call our Terraform backend setup script that we wrote earlier. We'll run the Terraform Setup action. We'll initialize our Terraform backend with our Terraform storage account. We'll validate our Terraform code. We'll generate the Terraform plan. Validate that our plan was successful. Publish the Terraform plan. And finally, we'll log out of the Azure CLI. The next and final job we'll define in this workflow is the Terraform apply job. Terraform will now use the deployment plan from the previous step to create our resources in Azure. This job also has several steps, some of which are similar to the previous job. Again, we'll have our checkout action, our Azure login, our setup authentication, we'll download the plan from the previous job, set up our Terraform, initialize our backend, run our apply, and finally we'll log out of the Azure CLI. Now we actually need to write our Terraform code. When doing so, I always reference the official Terraform documentation for my specific provider to ensure that I'm using the latest version and correct resource attributes. Start by creating a Terraform folder in the root of your repo. In this folder, we'll add our provider.tf file and set up the Azure backend. Next, create a data.tf file so we can reference attributes related to our Azure backend. Now create a variables.tf file. This file will be used to declare variables that our code expects. One thing to note is that we could provide default values in the variable definitions themselves. I'm not doing so because we are injecting sensitive variables through our GitHub workflow and using a dedicated TFVars file that we'll see in a second. To manage our variable values, create a Terraform.tfvars file. For our resource group location, I'll set my location to the East US2 region. I could just as easily add the resource group name here, but like I mentioned, we're injecting sensitive variables through our GitHub workflow. Let's visit the workflow file and update the step to inject our resource group name. The last Terraform file we need to add is the main.tf file. This will hold all of the code for our desired resources. Starting with storage, we'll define a storage account. We'll define an input and output storage container. And we'll define a storage queue for input events. Moving on to monitoring, we'll define a log analytics workspace and an application insights instance for observability into our function. Now on to compute. We'll define a service plan to host our function, and then we'll define the function itself. Lastly, we'll cover the events. Here we'll create an event grid subscription that watches for new files on the input container and routes these events to the storage queue that we defined earlier. Before we go any further, let's push our code to GitHub and deploy our resources to Azure using our GitHub Action workflow. Remember, you'll need to have the same secrets in GitHub but with your own values. The Azure SP credentials format can be found in the README of my repository. Head over to the Actions tab and kick off the workflow. Find your resource group in the Azure portal and ensure all of our resources have been created. Now let's develop our Azure Function logic. I'll start by creating a functions folder with some boilerplate code. Feel free to grab this from my GitHub and skip ahead. Here I'm creating a utils folder with two utilities. The first utility is for logging. It will allow us to log directly to the Azure App Insights instance that we stood up through Terraform. The second utility is a storage client that will allow us to easily interact with the Azure storage account that we're using in our event-driven subscription model. Like the last section, feel free to grab this code from my GitHub and skip ahead. develop our function, we'll create a new folder in the functions folder with our desired function name. The first file I'll add is a sample.dat file that represents the event grid message that this function will be pulling from the storage queue. The second file I'll add is the formal function.json file. This file will define our function and its trigger. In this case, we are defining a queue-based trigger. The third file I'll add is the function entry point script. This file is what consumes the queue-based trigger, parses the file URL, executes the core function logic, and returns a result. The final file we'll create is our helper.py file. I'm using this file to abstract the core function logic out of the entry point script to keep our code cleaner and more readable. Before we can test our solution, the last thing we need to do is write our GitHub deployment action for the function and deploy our latest code. Once the deployment has completed, you should now be able to see your new function in the Azure portal. It's finally time to test our solution. I'll prepare by opening some new tabs in the Azure portal. we'll need the function app, storage container, storage queue, and the event grid subscription. First, drop a test file into the input container and navigate over to the input queue. As soon as the message has been dequeued, you can assume the function has executed. Navigate to the output storage container and you should see the test file. Now let's observe our event and function since they tend to take longer to report metrics. Starting with the event grid subscription, you should see one matching and one delivered event. Looking at the function, you should see one successful execution and you can open it up for more log details. I hope this video has helped with introducing you to event-driven architecture and the scalable patterns to implement. Comment below what you're building with this event-driven approach. Thanks for watching.